Module 5 Mastery Assignment by Leslie Oy. Topic 1 Euler's Method. Euler's method is a numerical method for solving differential equations. We use this method when we are working with differential equations that cannot be solved with algebra. This produces an estimate based on the use of series of tiny tangent lines. So here are some steps in creating a Euler's method solution. First, you plug an initial value into a tangent line equation. Then, move your point one small step in the direction of that tangent line. We reset by calculating a new tangent line and move the point one small step x again. We then repeat this process until you get to the value you are trying to approximate. To organize our work, we can construct a table like the one shown below. For our tangent line, we usually put it in point-slope form. The delta x is our step size, or our slight change in x. Let's look at an example. Given the differential equation dy dx equals y, with our step size being 0.1 and the initial value being 0, 1, use two steps to approximate y of 0.2. Well, we are given that the slope of our tangent line is equal to y, and that the initial value is 0, 1. We will use Euler's method to approximate y of 0.2. To do so, let's organize our work into a table. So starting with our initial condition, 0, 1, we're going to get that dy dx is equal to 1. So our tangent line equation is going to be equal to y equals 1 times x minus 0 in parentheses plus 1. And our step size added to our x value is 0 plus 0.1. And when we plug that back into our tangent line equation, we're going to get a new y value of 1.1. So our next row will have 0.1 as x and 1.1 for y. So dy dx is going to be 1.1, and our new tangent line equation will be y equals 1.1 times x minus 0.1 plus 1.1. And when we add our x value to our step size, we're going to get 0.1 plus 0.1, and when we plug that value back into our tangent line equation, we're going to get a new y value of 1.21. Notice that we plugged in the x value of 0.2, so this qualifies for our estimate. However, what is the error in using Euler's method? Well, let's look at a graph. Here's a rough sketch of the differential equation we just looked at. Notice this underestimates the actual curve, and this makes sense because f of x is concave up everywhere, and therefore tangent lines to the curve will always lie below the curve. So if we had a function that was concave down, the estimates would always be overestimating. It is also important to note that estimation gets worse the farther from the initial point of tangency, so we should only use Euler's method for x values close to what we are given. Topic 2. Separable Differential Equations, or Diff EQs. These give us information about the rate of change of some function. We can solve for the function that has its derivative for a given differential equation. However, it is important to note that not all differential equations are separable. Here are some key terms you should know. Solution. This is a function that has a given differential equation as its derivative. General solution. This is a family of functions that all differentiate to a given diff EQ. Particular solution. This is a solution to a diff EQ given an initial condition. And an initial condition is any point on the solution curve that indicates which particular member of a family of functions is the solution to the given diff EQ. Here are some steps to follow when solving diff EQs. First, we need to separate. We will put all of one variable on the left side of the equation and all of the other variable on the right side of the equation. Then we integrate. We integrate both sides of the diff EQ. However, know that we only need to include a net constant of integration, typically on the right side. Then we can finally solve. We must then solve for the antiderivative equation for y. When we are given initial conditions, this means we will be finding a particular solution. Once we have the antiderivative, we can substitute our x and y values to solve for our constant of integration. Then we can substitute our constant of integration back into our antiderivative. Example 2. Solve the following differential equation with the initial condition y of 0 equals 3 and dy dx equals x squared over y. First, we need to separate our variables, so we will get y dy equals x squared dx. Now we need to integrate both sides. When we do this, we get y squared over 2 equals x cubed over 3 plus c. Now we can solve for y. So we're going to multiply 2 to both sides, and then we are going to square root. So we're going to get y equals plus or minus the square root of 2x cubed over 3 plus 2c. Then we can substitute our initial condition 0, 3. When we do so, we will get 3 equals plus or minus the square root of 2c, and then we can square both sides and get 9 equals 2c, and c equals 9 halves. So our general solution becomes y equals the square root of 2x cubed over 3 plus 9. Notice we got rid of the plus or minus sign in front of the square root, but this indicates that the y value will be positive.